The real number system, which of course is what we've been working with, well, all of your lives really. The real number system, how does this family fit together? So we have this set of numbers called the real numbers, which by the way means basically it can be placed on the number line, because the true name of the number line is actually the real number line. So real numbers can go on the real number line, and its symbol is the hollow R. The hollow R. Now, when you write the hollow R, you don't need to go all that way. We usually just put a double stroke on the vertical, like that, when you hand write it. So that represents the set of real numbers. Okay, so inside the real numbers, what do we have? We have these things called rational numbers, symbolized with the hollow Q. Why Q? Because Q stands for quotient. Quotient. See, all rational numbers can be written as a fraction, which is a quotient. Then we have the complement set to the rational numbers, the irrational numbers, which are simply numbers that aren't rational. There's not really a commonly used symbol for that one. So a way you can do it is actually combine those two other ones, R with a backslash Q. The backslash means not including, so the real set, but not including the rational numbers. It's very rare that we tend to write that, but anyway. Inside the rational numbers then we have fractions, and yes, I know I said all rational numbers can be written as fractions, but what I mean by fractions are ones that cannot be expressed as a whole number. So I'm talking about your 2/3, your 3/4, those sorts of things. And if it's not a fraction, then it's an integer. The symbol for integer, of course, is Z. I say of course, if you know German, you would know why. Zahl is the German word for integer. So that's why we use Z. I guess we don't use I. I'm only guessing, by the way. We don't use I because then people would assume we're talking about irrational numbers. It would get confusing. Now, inside our integers, we could have the natural numbers, also known as the counting numbers. Why is it called that? Well, if I said to you, start counting, where would you naturally start from? Hey, do you want to start counting for me?
One.
There you go. Thank you. See, wasn't that hard? So, well, another way of saying it is the positive integers. But the symbol for natural numbers is the hollow N. Mind you, we tend more to write it, Z with a plus on it. You probably see that more often than you do the N. Then we have this really weird number, and some people think it's not actually a number, and that is 0, which has a whole heap of its own properties, like you can't divide by it and things like that. So it sort of sits in there. It is an integer, it's not a natural number. Overlying some of these things are the negative numbers. You can have negative fractions, you can have negative integers, you can't have negative natural numbers, so it doesn't overlap there. And 0, again, it's this weird number. Is it negative, is it positive? Yeah. And you can have negative irrational numbers as well. But that's basically our set of real numbers and where everything fits together. Playing with real numbers, and one of the first things we play with are prime factors of numbers. So every natural number can be written as a product of its prime factors. 324, for instance, I could rewrite, of course, as 4 times 81, but they're not prime numbers. But 4 in itself can be written as 2 squared, 81, 3 to the power of 4, bang, we've broken it down into its prime factors. That leads us on to things like highest common factor, where we would write both numbers. If we wanted to find the highest common factor, you write it in terms of its prime factors, then you pull out the common factors. So here's 1,176, which eventually we get down to, there it is, 3 times 2 cubed times 7 squared, 252, which is 2 squared times 3 squared times 7. So the highest common factor, it's just like algebra, where we factorise out. And of course, when we're factorising, you always remove the lowest power. So in this one, 3 to the power of 1 is the lowest power, 2 squared is the lowest power that they both have, and 7 to the power of 1 is the lowest power they all have. 84 becomes the highest common factor. Then we have lowest common multiple. Write down both numbers in terms of its prime factors. That's the starting point again. But this time we write down all the factors without repeating. 48 and 15, or 48 to the power of 4 times 3, 15, 3 times 5. So we write them all down. Now this is like when we were doing algebraic fractions and getting the common denominator. So this time we pull out the highest power that needs to be there. So 2 to the power of 4 is the highest one there. 3 to the power of 1 is the highest. 5 to the power of 1 is the highest. So 240 ends up being that number we're looking for, the lowest number that both 48 and 15 go into. Divisibility test. Now, no cheating and looking at the sheet, by the way. That would take the fun out of this. Okay? How do you know if a number is divisible by something? By simply looking at the number. Well, here's the easy one to start off with. Anyone care to tell me how you know if something's divisible by 2? Yeah, it's an even number. Okay. 3 we actually talked about the other day. Remember we saw that, the digits have to add up to be a multiple of 3. 4. Yeah, the key is the last 2 digits. Now, why is the key the last 2 digits? Well, because when you get to that third digit, you're talking about the hundreds column, and of course 4 goes into 100. So it's the last 2 digits that are the key. If they're divisible by 4, then the whole thing's going to be divisible by 4. 5, come on, get yourself an easy one. 5 ends with 5 or 0. Ooh, 6. So 6 would be divisible by 3 and 2, so it's got to be an even number whose digits add up to a multiple of 3. Then you know it's going to be 6. Okay, the first really good one. 7. Without looking at the sheet. Does anyone actually know the divisibility test for 7? You double the last digit. Then you subtract from the other digits. And that answer should be divisible by 7. Give me a number, and please don't say 7, 14 or something really easy. Give me a number that we know is divisible by 7. Now it might mean grab your calculator and come up with a big number. 1,449 we're claiming is divisible by 7. So double the last digit. The last digit is 9, so I'll double it, and that's 18. Okay? Subtract it from the other digits. 14 minus 8 is, oh boy, thank you, 6. Now 126, now of course the question is 126 divisible by 7? Alright, let's do it again. Double the last digit, 6, 12, 0. Well, of course 0 is divisible by 7, 0 is divisible by everything, well, except 0. So yes, 1,449 is divisible by 7. Okay. Well, 8's a little bit easier than 7. And we can't do the little trick like we did for 6, of course, because we can't say it's an even number that's divisible by 4. Hang on. 4 is divisible by 2. So no, that doesn't work. But it is similar. But this time we look at the last 3 digits. And if the last 3 digits are divisible by 8, then the whole thing is divisible by 8. 9. The sum of the digits is divisible by 9. So it's very similar to 3. Well, that kind of makes sense because 9 is 3 squared. So sum of the digits is divisible by 9. Anyone care to tell me how we know if a number is divisible by 10? That's amazing. The last digit is 0. All right, another good one. 11. How do you tell if a number is divisible by 11? The sum of the even position digits is equal to the sum of the odd position digits, which is exactly what you were saying, of course. And they will differ by a multiple of 11. Or they'll be equal, of course, because then they differ by 0, and 0 is divisible by 11. So again, let's pick a number that we know. And don't go for 11 or 121. Let's make a big. Something divisible by 11. Sum of the even position digits. Oh, okay. 6. Sum of the odd position digits. 8 and 9 is 17. The difference between 6 and 17 is 11. So it's divisible by 11. And that's how you tell. I think that's where I stop. I mean, there are divisibility tests. We could keep going, but I think I stopped because I didn't really have enough room to write another one. Stop there. But it's those little tricks, patterns. It's like I was saying to you, maths is the science of patterns. You look for a pattern. All right. Fraction. Fractions and decimals then become quite important. Look, converting a decimal into a fraction is really easy because we use the base 10 system, and we know our columns. We've got the tenths and the hundredths and so on. So that's not hard. Fractions to decimals, well, if it's a terminating fraction, again, not hard because we know that just means division. So if I wanted to work out what it was, 3/4, I'd go, oh, what's 3 divided by 4, and work out that calculation and get it. Recurring decimals then become interesting. How do we turn that into a fraction? So let's do ones that we know, at least I hope we do. 0.6 repeater, which we know is, of course, 2/3, 6. Here we go. Here's a way of doing it. I say a way, in reality it's not how I do it, but anyway. We know 0.6 repeater is 0.6, and it would just keep going on forever. So I'll let x equal that. I want to find what x is, but I want it as a fraction. I don't want it as a decimal. So in other words, x is 0.6. Oh, I'm enjoying that so much. I'm just going to multiply both sides by 10. And it becomes 6.6. And what I've got now is simultaneous equations where I can get rid of the problem. And the problem is this repeating decimal, which is going on infinitely and never gets to the end. But what I do know is in every single position there's going to be the number 6. So it'll always cancel, get 0, 0, 0. So I'm left with 9x is 6. Oh, x is 6 on 9. So there's our answer. 0.6 repeater is 2/3. That's a way of doing it. Now, if there was two numbers, I could use the same idea. So 0.81, 81, 81, 81, and so on, if I let x equal that. Well, this time, multiplying by 10 is not going to work, because I want the same number in the column. So in order to do that, I really need to move that decimal point 2 places. In other words, multiply by 100. But now the columns are the same after the decimal point. I can do the subtraction. So we get 81 on 99, simplifies down, 9 on 11. What about if not all the numbers are repeating? So I've got 0.3 and just the 2 and the 7. So in other words, it's 0.3, 27, 27, 27, 27. So that's what I'll let x equal. Okay, I want to line it up so they're the same. I basically need to multiply them by 100 again, because there's two numbers repeating. I want to move that decimal point 2 spots. So I get 32.727. So when I do a subtraction here, I get 32.4. Well, we don't normally write fractions with a decimal. I mean, it's usually one or the other, not both. So 32.4 over 99 would be the same as 324 over 990, which simplifies down to be 18 on 55. That's not how I do it. Okay, it's about spotting a pattern and then using that pattern to your advantage. Okay, so let's go back to 0.6 repeater. Okay, I would just look at that and say, well, hang on, 6 is recurring, so that's what I'll put on the top of the fraction. 1 9 on the bottom. Why put a 9 on the bottom? There is one number recurring, so I put 1 9 on the bottom, and there's my answer, 6 on 9. So 0.1 repeater would be 1 9, 0.2 repeater, 2 9s. You know, all the way up to 0.9 repeater, which is of course 1. 0.81 repeater, using the same idea, I'll put 81 on top because 81 is recurring, but on the bottom I'll put 99. Two numbers are recurring, so I put down 2 9s, and by 2 9s I don't mean 18, I mean I physically put 2 9s, 99, 81 on 99. There's my answer. So if I had something like this, 0.7134, all the numbers are repeating, now I can just look at that and go, oh, okay, that's it. Bang, there's the answer. 7,134 over 9999. 4 numbers repeating, put 4 9s on the bottom. That simplifies down. Okay, what about the one where there was a number that didn't repeat? All right, on the top goes 324. Where did I get that from? 327 minus 3. So I write the numbers down, but I subtract the number that's not recurring. 3 is the number that's not recurring, so 324. On the bottom, I'll put 990. Why? Well, two numbers are recurring, so I'll put 2 9s down. But there's a number that's not recurring, so I'll put a 0 there for that. Now, I'll put the 0 at the end of the number, because if I put it at the front of the number, it's still just 99. There was no point of putting the 0 there, so it goes at the back end. So 990, 18 on 55. So if I had this, 0.1096 repeater, and only the 9 and the 6 are repeating, I now know that that's going to be 1,086 on the top, because that's 1,096 minus 10, and on the bottom, I'll go 9900. Two numbers repeating, two numbers are not. There's my answer. Bingo. So using patterns to our advantage. Spot the pattern, save yourself some time. Okay, so some questions out of 2A. Also some from the old Cambridge book as well. I threw a couple of those in there for a bit of fun.